Hello. So I hope you were able to solve this problem, and let's see and compare your results. So caffeine is another weak base, and it is let's check the structure of caffeine to find why it's considered a weak base when we add it in water. It's not going to be very soluble in water, but it's going to behave as a base. Look at the structure. What do you find there? You find the nitrogen. But what nitrogen will give the basic properties to this molecule? What is a base? Base is a substance that is accepting a proton or will accept a proton. So tell me what nitrogen is willing to accept a proton, a hydrogen. What about this one? No, all right? All bonds are busy here, and we don't see the two pair of non-bonding electrons there. Isn't the ring? Here, no. Here, no. What about here? This is more ready to accept a proton there. Right, so it's a basic. It's a weak base. The problem says 0.15 molar solution of caffeine at 25 degrees Celsius has pH of 8.45. Find the Kb of caffeine. So what is your strategy? Write down what is given. So we know initial concentration of the base. For simplicity, I will recommend you don't have to write the whole formula and find what is the caffeine. This is just extra information. This is true, this caffeine is a base and behave that, but you can simplify this. Okay, this is my base. All right, or you can call, well, let's use B because you use C, you can get confused with carbon. So B plus H2O in equilibrium with B plus, HB plus. H, the proton that comes from water, and the rest is the rest of the molecule. Plus OH that comes from here, from the water, OH minus. AQS, 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 and this is liquid. All right, so we know initial concentration of the base, which is 0.15 molar. We know the pH, which is 8.45, and the question is find Kb. What would you do? Yes, you need to write the equation and you need to find the ice table. So the ice table will be very quickly 0.15 here, 0.15, 0, 0, 0. The change is going to be minus x, x, x plus x, right? And the equilibrium will be 0.15 minus x, x and x. And that's why we need these equilibrium concentrations. We need those to find Kb. And the Kb expression will be concentration, equilibrium concentration of Hb plus, this one, times concentration of OH minus over initial concentration of the base. Sorry, equilibrium concentration of the base, this one here, 0.15 minus X. So the clue here is to find X. To plug into this equation, because it's going to be X squared over 0.15 minus X. That will give you the value of Kb. So let's find X. How do we find X? And remember, this time, since we have a weak base, X is equilibrium concentration of OH minus. How do you find X? From here, on the pH. But remember, this is pH. This gives you concentration of H plus. And we don't need H plus, we need OH minus, because this is a base. So there are two ways to do it. One, find pOH and find anti-log of pH. 10 to the minus pOH gives you concentration of OH. Or find concentration of H plus and use this formula, concentration of H plus times concentration of H minus equals 1.0 times 10 to the negative 14. You can use either this one, or you can use pH plus pOH equals 14. So you want to use concentrations, use this one. You want to use pH, use, this is pOH. pOH. All right, so from here, what is pOH? pOH equals 14 minus pH, 8.45. How much is that? That is 5.55. 5.55, that's the pOH. Now that we know the pOH, how do you find concentration of OH minus? You say concentration of OH minus equals 10 to the negative pOH, 5.55. So you do the same thing I showed you in the calculator to find concentration of OH minus. And that will be your X, all right? Let me show you again. So it's 5.55. So we clear this. We say 5.55. We change the sign for that because it's negative 10 to the negative pOH. and then do 10 to the x. And that is 2.81 times 10 to the negative 5. Oh, negative 6, right? Sorry, I think yes, 10 to the negative 6. 2.81. Which is here. (2.81 times 10 to the negative). That's the concentration of OH minus, which is your X. Now we can plug that over here. So Kb equals 2.81 times 10 to the negative 6 squared divided by 0.15 minus 2.81 times 10 to the negative 6. And what do you get? Just do the operation, it's very simple. Very simple calculation. And let's see what we get. 5.3 times 10 to the negative 11. See? We just did it. That's the answer. Do it yourself, do your own calculations, rewrite everything on the piece of paper, step by step, and then compare to these results. That's the way to do it. All right. So the treatment in terms of calculation is similar for weak acids and weak bases. Finding Kas, finding pH, finding percent ionization is similar. All right, now let's find the relationship between the conjugate acid and conjugate bases, and the relationship with the Ka and Kb of the conjugate acid-base pair. This is important, and it's going to play a big role later on when we work with buffers. That's the next chapter. So let's see this case. For a strong acid, hydrochloric acid. So we have here a strong acid and a weak what? What is this? Acid or base? Well, if this is acid, because we know hydrochloric acid is acid, therefore this has to be a base. And water is always weak base or weak acid. And since this is strong, it will ionize 100%, complete ionization, so no equilibrium, to form hydrogen ion and cation, Cl minus here, the chloride ion. This is a conjugate acid of that weak base. How strong is this? This comes from a weak base, therefore this is a strong. conjugate acid of this base. What about this here? This comes from strong acid, therefore it will make what? Weak or strong? Weak. Conjugate base. Too weak to react with water. Be careful. Strong acids forms very weak conjugate bases, too weak to react with water. Since we have a water around, this is a aqueous solution, so water is the solvent. Let's see what the chances are that this chloride ion that comes from the strong acid reacts with water. What do you say here? None. Not a chance. Why not? Because it's too weak. Again, conjugate base of a strong acid is too weak to react with water. So no reaction occurs with water. So they say there's no hydrolysis there of water due to this secondary reaction. So there's no secondary reaction for strong acids. What about strong bases? You do the similar analysis. The strong base will produce a weak conjugate acid, too weak to react with water. So no secondary reaction with water will occur. However, for the case of weak acids and bases, the situation is totally different. And we need to take that into consideration when we have these solutions of acids and bases. We need to analyze the strength of the conjugated acids or conjugated bases that comes from the weak acid of the weak or the weak base. So there's always relationship between the acid and the conjugate base of the acid, or between the base and the conjugate acid of the base. Let's check this example. HF, we mentioned it before, is a weak acid. So let's write it here. It's a weak acid reacting with a weak base. The weak base forms a strong conjugate acid. And the weak acid makes a strong conjugate base. You see the negative sign here, the extra pair of electrons? Well, these are base. That's the anion. The salt of a weak acid is always strong. Has negative charge, and that loves protons, is anxious to get protons to neutralize that charge, to this one. put the equilibrium to the left. So here the reverse reaction is the most important. That's why this is a weak acid, because the weak acid is not making a lot of this. At the equilibrium, you won't find a lot of those. As you notice, when you find X, very small amounts, and the values of KAs Ka for the reaction will be concentration of H3O plus times F minus over initial equilibrium concentration of the HF. And these numbers are very small. And we know the number, I think I have it next time, 1 point something times 10 to the negative 4. I remember it was 10 to the negative 4. Right, so that's the equilibrium expression for that. So at the equilibrium, very small amount of this. So what happened with this strong conjugate base that comes from here? It's strong enough to react with water. So there's a secondary reaction happening there. Not only the ionization, but also the reaction of the strong conjugate base with the water that is present there. So that reaction is F minus the strong base with water. In this case, it's going to be weak acid to form HF, the weak acid. And guess what is this? A strong conjugate base. That's the secondary reaction. That happens once the F minus is formed here. So this reaction is the reaction of a base. Yeah. So we have one reaction of the weak acid we are adding to the solution, but the weak acid forms a strong conjugate base, and that strong conjugate base forms a second reaction, produces a second reaction, which is very important. And that will be a reaction of a base, right? This is a conjugate base. So this one, since the way it's written is a base, it has a KB. But this, be careful here, and that's the part I need to make a lot of emphasis. This KB is the KB of the conjugated base of that weak acid. So those are related each other. If we write this expression from here, we have concentration of HF times concentration of OH minus over concentration of F minus. So at the end, we'll see that these two are related. And we want to know, we know this value here, and we want to know this value. of the Kb of the conjugated base. So what is the relationship between these two? We do an operation here. If we operate here and we add these two equations, what do we get when we add these two equations? We find, let's add these two equations. You will notice that this is a reactive, but then it's a product here. So they cancel out. And we have water. F minus is a reactive here and is product here. So they cancel out. So what do we have? The net equation is H2O in equilibrium forming H3O plus OH minus aqueous, and these were two, right? 1 and 2. And this one, we know this one has a special equilibrium, Kw, 1.0 times 10 to the negative 14. So remember one of the properties of equilibrium? What happened with the equilibrium constants when we add two equations? You can multiply. So when we add the equation 1 and 2, the new equation is the multiplication of Ka and Kb. So Ka times Kb equals Kw. A beautiful equation that will help you to solve a lot of problems. But you have to be careful because this is not any Ka and this is not any Kb. This formula applies, and be careful with this, only and only when we're talking about the secondary reaction of the conjugate base or a conjugate acid, depending on what you have initially. If you have a weak acid, the weak acid will form a strong conjugate base, strong enough to produce a secondary reaction, and the secondary reaction has a Kb. So these are related. This applies only for the situation. This is not, you cannot apply this when you have Ka from one acid and Kb for a different base. No. Any base? No. Any acid? No. Only when they are related this way. For the case of the weak bases, so you will have a weak base forming a strong conjugated acid. That conjugated acid is strong enough to react with water to produce a second reaction, and that will have a Ka. So it's always Ka and Kb. So Ka times Kb equals Kw. I'll show you how to use this one, and I'll show you another case with weak bases. So important to know, to remember, that strong acids produce a weak conjugate basis. Weak enough or too weak to react with water. Weak acids, on the other side, produce strong conjugate bases strong enough to produce a secondary reaction. So in this case, you will have the Ka, you will have the Ka of the weak acid, and you will need probably to know what is the Kb for that conjugate, strong conjugate base. The thing here is that you won't find a list of Kb's of those conjugate bases. There are no lists. You only find Kas of the weak acids or Kb of weak bases. You won't find Kb's of conjugate bases. But that's not a problem, because I just gave you a beautiful formula to find that. The formula says that Ka times Kb equals Kw. So from here, that's what you want to know, right? So you say Kb of that conjugate base equals Kw, which is 1.0 times 10 to the negative 14 over the Ka. That is listed. HCN, I think I show you in the list of weak acids. It was there. Hydrocyanic acid. We know this number, Kw, over this, which is known, will give you the Kb of that conjugate base. Remember, you won't find that Kb on list anywhere. You have to find it yourself. And on the other side, for bases, you have a strong base, it will form a weak conjugate acid. Too weak to react with water. So there's no secondary reaction. However, we have a weak base. That weak base produces a strong conjugate acid. Strong enough to produce a secondary reaction with water. Therefore, you will know the Kb for this because it's listed. This is actually, remember this 1.8 times 10 to negative 5, we just did it before. But you won't find the value of Ka of this conjugate acid for the secondary reaction. And that will be, let me write it here. This is important one. The secondary reaction, we know the first one, the first reaction of NH3 plus water forming NH4 plus OH minus. But the secondary reaction is going to be that conjugate acid plus water. Remember, this is a strong conjugate acid. Therefore, this is going to be a weak base. It's a base, and we know water is always weak. In equilibrium with, so this is the acid and this is the base is going to accept proton. It's going to be NH3 aqueous plus H3O plus. And this one has Ka. This is the Ka I was talking here. Ka of the strong conjugate acid. And you won't find this on the list. So how do you find this? You need to find it yourself. You need to calculate it yourself. Very simple. So Ka of the conjugate acid equals Kw of Kb, which is given in tables. And why do you want to know the Ka? Because you want to know how much hydrogen ion is the secondary reaction producing. Because this is strong. And that will change the pH. Also, the base is increasing the pH. But this secondary reaction will introduce some hydrogen ion to reduce the pH, to bring the pH down a little bit. So finding the pH of this weak acid, weak bases is a little bit tricky, and even more tricky when we're talking about salts. Not all salts are neutral. Some salts are acidic and some salts are basic. For example, a salt containing NH4 ions, for instance, NH4Cl, ammonium chloride. When you dissolve this in water, we produce a solution with certain pH. So what pH of that is going to be? Is this a acidic salt or basic salt? If you look at this, you will notice that when you dissolve this in water, this salt will dissociate. It's not going to ionize because it has already the ions, NH4 plus and Cl minus. Water just going to help to dissociate into ions. So once in water, you will have NH4 aqueous, exactly this one, aqueous. And you know this is strong enough to react with water and to produce hydrogen ions. Therefore, this is acidic salt. So be careful. A lot of people think salt, dissolved salt in water, is neutral. No, it's not. It depends. Depends on where the salt is coming from. So here we are going to find a basic rule. And people get confused because we always use this table salt, sodium chloride, as a reference. This is neutral. Neutral. Because if we add salt, sodium chloride, table salt, into pure water that has pH 7, you add that salt to that pure water and the pH of that solution is still 7. Why? Because it's neutral salt. And why this is neutral salt? Simple. Because sodium is too weak, sodium plus. This one dissolves, dissociates in water to form Na plus aqueous plus Cl minus aqueous. So you need to think where the salt is coming from. Sodium, the sodium portion, sodium plus, comes from a base. What base? NaOH. And Cl, the anion, comes from the acid. What acid? HCl. Remember, the reaction between a base and acid is neutralization, and that produces a salt plus water. And everything aqueous. Aqueous. All right? Don't forget to write the aqueous. You need to remember that. But who's sodium? Sodium is a strong base, therefore it will produce a weak sodium plus ion. Too weak to react with water. So no secondary reaction with water. And who's Cl minus? Where Cl minus coming from? Comes from the strong acid, producing this anion, conjugate base, too weak to react with water. So on this side, also too weak to react with water, so no secondary reaction, generating extra OH minus or extra H plus, OH minus or extra H3O plus. As a result, we have a neutral solution, but this case is different. As we saw here, NH4 comes from a weak base that produces a strong conjugated acid that is strong enough to react with water, and that secondary reaction is able to produce extra H3O plus, and that brings the pH down, changes the pH, making the solution more acidic. pH goes down. So this salt is acidic. And the previous one is similar. I didn't write the secondary reaction, but let's do it here. The first reaction is the reaction of ionization of HCN, reacting with water, producing H3O plus Cn minus, the cyanide ion, which is strong enough to produce a secondary reaction, to cause a secondary reaction. I'm going to write it here. The first one, you can do it yourself. But the secondary reaction, let me remind you how to do that. We have the Cn minus that is product of the first reaction. Aqueous plus water, liquid in equilibrium. What happened here? This is a strong conjugate base. Therefore, this is a weak acid. What is the product here? This is the base. It's going to accept the proton to form HCN, and the weak acid, since donated the proton, becomes OH minus, which is a strong base. Remember, OH minus, the hydroxide ion, is the most basic species in water. So what is the consequence of the secondary reaction? the concentration of OH minus being produced by the secondary reaction increases the pH. The weak acid, since this is acid, it will bring the pH down, lower than 7. However, there's a secondary reaction that will bring the pH a little bit back up. So it's tricky, right? To figure the pH of those weak acids or weak bases. And we need to take into consideration the strength of the conjugated acids or conjugate bases. This is what I did before. So you can go over this. I already did this. Here they're showing with acetic acid. The acetic acid reacts with water to form hydrogen ion, and the conjugate base is strong, very strong acetate ion, strong enough to react with water. The reaction of this acetate ion with water, and remember I like to represent it in the more simplified way. So this will be HAC aqueous plus water in equilibrium with H3O plus aqueous plus AC minus, the acetate ion. And this is the Ka for that equilibrium here. And the second one, the secondary reaction, this is the primary reaction, and this is the secondary reaction, the reaction of the strong conjugate base, acetate. These are related because this is consequence of the first one. So for the second one, the simplified way is AC minus this one, the acetate ion, strong enough to react with water, liquid, in equilibrium with HAC plus OH minus, this is aqueous, and this is aqueous. And this is the equilibrium expression for the secondary reaction, and you see they're related there. You see they cancel out here, right? When we add these two equations, Ka and Kb, you multiply Ka times Kb. Multiply these two, and you will see the result is just Kw, because they cancel out. This one cancels out with this one. When you multiply these two expressions, and this one cancels with this, and what is left? H3O plus, concentration of H3O plus times concentration of OH minus. And what is that? Kw. And that's the one I did before. Like this. And this is the equation I showed you before. Very useful equation. So now we have acetate ions. This is a conjugate base. So you can find the Kv for that. How do you find this? Well, you need to find the Ka of the acid that made this ion. Or acid, that's the key here, to find who's making the conjugate species, either as acid or base. So in this case, the acetate makes sense to think that this one is coming from acetic acid. What about this? This is a salt of amine with only one Ch3, one carbon. So it's methylamine. So this is acid, right? This is a conjugate acid. So the conjugate acid, Ka of the conjugate acid equals Kw over the Kv of methylamine. This is a conjugate base, and the Kb of the conjugate base equals Kw over the Ka of the acid that made this. This is F minus, which is a conjugate base. So it has a Kb of the conjugate base, which is what? Kw of the acid who made that, which is Ka. In this case, HF, hydrofluoric acid. Now, who's this? NH4 is the ammonium ion. It's a conjugate acid, therefore it has a Ka of that conjugate acid, which is Kw of the base who made it, in this case ammonia. And we know Kb of ammonia, like that. And since we know the values, just go to the table, find the Kas, Kbs of the original weak acid or weak base forming these conjugate acids or bases. And here are the numbers already. Those numbers were taken from the previous table. So you stop the video, rewind, and check the values, plug, find it yourself, and then come and compare here. Don't cheat. Don't look at these numbers yet. All right. The polyprotic acids, I defined those already. But there's a little treatment, something that we need to realize for the polyprotic. For example, this one, carbonate, carbonic acid, H2CO3, is a diprotic acid because it has two acidic hydrogens that can be ionized. But when you have a diprotic acid, that means the acid will ionize in two steps, 1 and 2. And we call first ionization, second ionization. The first ionization produces the first or releases the first proton, leaving behind this species, HCO3 minus, and this is the ion that you very well know is bicarbonate. This is carbonic acid, and this is bicarbonate ion, or hydrogen carbonate ion, either way. So that means this species still has one hydrogen that can be donated. That's why it goes, this one comes here, it's this one, and that one goes to a second ionization step. So the ionization of diprotic ions goes through two ionization steps. Every one has its own Ka. So that's why you call Ka1 for the first step and Ka2 for the second step. And when you compare the values, you will notice that the most important always is going to be the first ionization step, meaning that most of the hydrogens will come from the first ionization. For a lot of cases, you will know the Ka of the second ionization is a very small number. That means the second ionization will produce very little amount of those ions. So the total equilibrium concentration of H3, total equilibrium concentrations will be what? The equilibrium concentration, the concentration of H3O plus from the first step plus what you get on the second step. Remember, for most of the cases, most of the hydrogen ions comes on the first step, and you will notice that just by checking the magnitude Ka1. And the second step will give some extra concentration of H3O plus. So we have to do step by step. Similar, just independent, find what is the first equilibrium, how much is this, and then use that for the second equilibrium. If you have polyprotic acid, like another example of diprotic, for example, H2, this is strong, H2SO4. It's strong and most of the ions comes on the first step. However, since this is a diprotic, the ionization goes through two steps. Another example of weak, like for example, some weak organic acids can have more than one proton, like citric acid, tartaric acid, malic acid, they have more than one proton, so they go through 1, 2, or 3 steps. For the case of phosphoric acid, H3PO4 is a weak acid and it's polyprotic, it has 3 protons. So that means for the ionization of this polyprotic, you need to go through a 3, or you need to write 3 ionization steps, 1 per proton. So we have this aqueous that will be plus water in equilibrium to release the first proton. So you get the first hydrogen ion plus what is left after this species gives off 1 proton. Yes, H2PO4, and since 1 proton was lost, it gets 1 extra negative charge. That's the first ionization. And the Ka, you say Ka1. And it's given. You find this on tables. Second ionization, this one that is being produced here goes to a second ionization. So you write that one here, H2PO4 minus aqueous plus water for the second ionization. And that, what happened here? Produces another hydrogen ion here. Plus, what is left? This one is going to lose one more proton. It's here. And what is left? H, PO4, 2 minus. Aqueous, and this one has Ka2 given. And then, once this is formed, this will go through a third ionization step. So you take that right here and show the third ionization process with water in equilibrium to form another hydrogen ion using the hydrogen, and what is left? Plus PO4 minus, 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 3 minus. And this one has Ka3. Interesting. Now, how much hydrogen is being given here on this step or second step depends on the value of Ka. Again, if you compare these values and you see usually the first ionization is the one, is the highest value, highest magnitude. That means that most of the hydrogen comes from the first step. You will see, I'll show you the numbers later. Also, it is interesting to see that those salts, those conjugate bases, can be amphoteric. You have a salt of this, or salt of this, or salt of this, they can form 3 different salts. That's why phosphorus is very useful making buffers. In biology, they use a lot of buffers to keep the pH, the right pH for the biological processes. Phosphate ion plays a factor keeping, stabilizing the pH in our bloods. We learned at the beginning that the pH of blood, human blood, is between 7.3, 7.4. So the phosphate buffer helps to keep the pH balanced. And this can be amphoteric. That means this salt, once it's formed, can go that way or can go this way. So it can gain a proton behaving as a base, or can give off a proton behaving as an acid. Similar with this. This can go back, gaining the proton, so that will be a base, right? If the reaction goes that way, to the left, this will behave as a base. But that behaves this way, to the right, and on the third reaction, meaning giving off protons, it will be an acid. So they are amphoteric, because they can gain acid, gain proton, or lose proton. Same thing with this. It can gain proton or can lose proton. That means can be acid or can be base. Therefore, we can say those species are amphoteric. Some examples of polyprotic. I mentioned a sulfuric acid. Sulfuric acid is a strong acid. However, the Ka2 is small, so the hydrogen sulfate ion behaves like a weak acid. Oxalic acid has 2 carboxylic groups there, having 2 acidic hydrogens. I look at the value of the second Ka compared to the value of the first Ka. So the first ionization is very important, as usually, compared to the second ionization. Sulfurous acid is a weak acid. Look at the Ka of the first ionization and look at the Ka for the second ionization. Very small. Proba ascorbic acid, which is the vitamin C. Has two hydrogens that can be ionized. This one and this one here. This carboxylic here, and this is the second carboxylic there. So it can be ionized. Look at the Ka for the first one and Ka for the second. So the second ionization is minimum. More here, carbonic acid. Look at the value for the first ionization, times 10 to -7, and the second ionization times 10 to -11. Hydrosulfuric acid, same thing, H2S. You can compare that. The phosphoric acid I was mentioning, for the first ionization is -3. Look at the second ionization, look at the third ionization. So the most of the hydrogens, H plus, hydrogen ions, comes from the first ionization. And it's a weak acid. So oxalic acid is a polyprotic. In this case, has two acidic hydrogens there. We need to calculate the concentrations of all species at equilibrium if we start with 0.10 molar solution at 25 degrees Celsius. So we write the first ionization, and this is the Ka for the first ionization. We write the equation for the second ionization, and this is the Ka2 for the second ionization. And then we do ice table for each one. And the first one, the same way we just did it before, same ice table for the equilibrium. You had the initial, you had the change, find the equilibrium, find X. And you can make the approximations to find X. Once you find X, you can apply that to the second ionization. So that will be the initial, your X here is the initial for your second ionization. Second ionization reaction here. So the equilibrium here, X and X, we're talking about this one. That's the initial for the second ionization. You already have some of the acid from the first ionization, that's X, and you have nothing of this. This is the change. In this case, we use Y to make it different from the first ionization, because those two numbers may be different. So minus Y, plus Y, plus Y. At the equilibrium, you find initial, which is X, minus Y, the change, that's the equilibrium concentration of this. X plus Y, concentration of, total concentration of H3O plus Y. You plug those over here for every one, K1 and K2, that's X. That's the calculation, we do the approximation, find X for the first ionization, first ice table, find the ionization, which which is 81%. Wow, that's a lot. That means that for the first ionization, look at the percent ionization is 81%. That goes beyond about the 5% rule. Meaning what? We cannot do the approximation. Sorry. So we have to go back and do it solving the actual quadratic equation. So we cannot do this, we cannot round this off to 0.10. We have to actually solve, we have to actually solve the equation. This equation. Because as you know, we did the approximation, we plugged into the ionization, percent ionization, we find 81%, a way to be bigger than 5%. So that means we have to go back and we have to do this using the quadratic equation. Sorry, but that happens. So here is the solution. Plug again, everything. Solve the quadratic equation, and this is the route that makes more sense once you solve for quadratic equation. Plug that into the first ionization. These numbers that were plugged over here. This is for the first case. And then we are going to use those numbers to plug it here to find the second equilibrium. X in that case was 0.054. Then you plug that into the second one. That's the initial now. Find Y, same thing. Plug it into the equilibrium expression. And here we try again. We try to do the approximation, saying Y, we're expecting Y to be very small. Let's see. Compare Y. Yes, Ka2 is very small. So we're expecting Y to be very small. So probably we can do the approximation here. And we can solve for Y. So Y equals 6.1 times 10 to the negative 5. Let's prove. Percent ionization is 0.11. Yes. Oof. Less than 5%. So we are good. We can use this number. We can keep on going. Plug that into the equilibrium expression here. And these equilibriums, that's Y. Plug it here, and then you can plug that into your KB, which is here. And find all the, finally get the, sorry, you don't have to plug it into the equilibrium expression, just find the final concentrations for everyone. And these are the answers. So that's how basically you do it when you have polyprotic acids. Now for molecular structure, it's important to check the structure of the acids and bases, because that can give you an idea of how strong is the acid or how strong is the base. Especially when you compare with acids of non-metals in the periodic table. So to see what is the periodic trend of the acid strength, or if we are looking for metals, metal oxides, making bases, you can also check what is the periodic trend of these metals to make bases, either strong or of the strength of the bases. So the strength of an acid is measured by its tendency to ionize, right? Strong means complete ionization, weak means a partial ionization. And that is explained through the bonds in the acid. If that bond, hydrogen and the other element is weak, very weak, ionizable, so the acid is strong because it can be ionized. If that bond is not too weak, it's somehow a little bit strong, so it's hard to ionize. So the acid will be weak. And the factor playing there is polarity. If there's a high polarity in the molecule, I mean, there's more tendency to ionize, to give a strong acids. But the polarity is lower, so there's not tendency. The tendency to ionize is lower, forming weak acids or weak bases. For hydrohalic acids, that means hydrogen attached to a halogen, the strength can be easily predicted if we look at the periodic table. Look at these acids, and they are called binary acids because they are made of only two elements. Those are halogens, and they are in the order, same order you find them in the periodic table, from top to bottom in the same group, group 17 of the periodic table. Look at the bond enthalpies to have an idea of how strong is the bond between these two elements. As you can see, the strongest bond is this one, HF, with very high bond enthalpy. And the bond enthalpy decreases from top to bottom in the group. In other words, this bond here is very strong, and the tendency to ionize that is low, producing weak acids. However, here, there's more dipole, and also you have to take into account the electronegativity. Fluorine is holding electronegativity 4.0 in the scale of Pauli's scale of electronegativities. That indicates also the ability of fluorine to attract and hold these electrons, making very strong bond. On the other side, this represents a weaker bond here, making a strong acid. And also the relative size of those, remember the size of these atoms increases from top to bottom. So making this very polar also. So that makes a strong acid. For oxoacids are acids that contains not only hydrogen, but also oxygen. Like nitrous acid, carbonic acid, nitric acid, sulfuric acid, and phosphoric acid, and phosphorus acid. This is a strong acid, and this is a strong acid. All others are weak acids. Here we have these two oxoacids. This one, the central atom is chlorine, and in this one, the central atom is bromine. Remember the position of chlorine and bromine in the periodic table? Chlorine is on top of the group, above bromine, has higher electronegativity than bromine. So the acid strength increases with increasing electronegativity. So we can classify HClO3 is stronger than HBrO3. So just by looking at the position of these two central atoms in the periodic table, this is on top, this is on the bottom, on the same group, and electronegativity increases from bottom to top. So chlorine has higher electronegativity than bromine. When oxoacids have the same central atom but different number of oxygen atoms, so how do you figure which one is stronger? This one has only one oxygen in its structure. This one has two. So the oxidation number, look at the oxidation numbers. In this case, is +3. Here, this has 3 oxygens around the central atom, chlorine. The oxidation number is +5. This one has 4 oxygens around chlorine, and the oxidation number for chlorine, that is +7. So the acid strength increases with increasing oxidation number. So now you can organize those. This is stronger than this, than this, than this. So here you have that's how you organize the strength of the acids for this series of oxoacids having chlorine in the center as a center atom in the structure. So I'll show you some examples here how to do it. Here they have different central atoms in the first case, And then the second one has the same but different number of hydrogens. Oxygens. The first one, different central atom. So look at the position in the periodic table. So in the periodic table, this chlorine is on top, in the same group, then bromine, and the bottom is iodide. Electronegativity increases from here to there, from bottom to top. The acid strength increases with electronegativity. So, you know, this acid is stronger than this, and this, than this. Here, the same central atom with different number of oxygens. Has higher number of oxygens, therefore has higher oxidation number. What is the oxidation number of nitrogen there? And the first one. So the oxidation, this is oxidation number is -2. This is +1. So total here you have -6. Therefore, the oxidation number here is +5. +5 + 1 is +6 - 6 equals 0. Then we have a neutral molecule. Well, here is -2. So 2 times -2 is -4. This is +1. Therefore, this is +3. So the acid strength increases for the oxidation number and is related with the number of oxygens. This is stronger than this. Nitric acid is stronger than nitrous acid. So that's how you do the analysis. All right. I'm going to leave this for the next video.